All right, let's talk about logistic regression. So this is one of those very powerful statistical tools that we can use to predict dichotomous outcomes. And it's a test that allows us, when we have more than one or more independent variables, to help us predict that dichotomous or binary outcomes, say, for example, postoperative nausea and vomiting. And the goal of logistic regression is really to help find the best fitting model to the data. And it works the same way as multiple regression, that you're generating beta coefficients and their standard errors and p-values. You're essentially developing this formula to help predict what they call a logit transformation of the probability of presence of the outcome that you're interested in, say in this example, nausea and vomiting. It also has the same advantage as multiple regression in that you can include categorical and quantitative variables in your analysis. So here's just an example of what a formula would look like. It's taking the logit probability, which equals the intercept plus the slope of the different regression coefficients, plus it also includes an error term. And what it does is P is that probability of the presence of that characteristic, say in that circumstance, nausea and vomiting. And it's the logit transformation is logged as the odds. So you have the probability over 1 minus the probability, which is the probability of the absence of that characteristic, is an odds ratio, as an odds, and then you take the logit of that. So what the primary result that we're looking for with logistic regression is it presents odds ratios, which we talked about earlier. And so the regression coefficient, when it's calculated, is the estimated increase in the log odds of the outcome per unit increase in the value of the exposure. And what it does is it takes the exponential function of that regression coefficient, and then that's essentially allows you to calculate that odds ratio, just like you would with a multiple regression in terms of per unit increase in exposure to that particular variable. So this just shows you some information that you might see on a statistical software, where you're looking at the variable that you're trying to predict as a binary, usually coded as a 0 or 1 in your data set. And you have a series of independent variables. And then you have the methods in which we might enter those variables. Remember last time we talked about stepwise regression, and this is where it's entering the variables sequentially and then checking and removing variables that become non-significant based on a pre-established p-value. And then what you can do is you go further and you can develop a classification table in cutoff values, and that's where that ROC curves come into play. And what it's doing is it's taking the observed values of the dependent variable and the predicted values, and they're cross-classified. So with logistic regression, it has it has some assumptions, just like all the other statistical tests, is that the predictor variables should not be highly correlated with one another. So that's that concept of multicollinearity that we really don't want with regression. Sometimes you need really large sample sizes to be able to predict these outcomes. And certainly the more variables you have included, the larger the sample size you need. And it also can calculate a goodness of fit of the model, which basically helps us it tells us how well that model describes the outcome that we're interested in. Sample sizes, I mentioned, tend to need to be much larger, and calculating sample sizes can be a little complex. So I'm not going to read over this slide for you, but what you can do is you can pause the video and read over this, and I just present it so that it gives you a little bit of understanding of what goes into calculating a sample size for a logistic regression. All right, let's just look at some examples here. So here's from an article I pulled out of Critical Care in 2005 that did a nice job of explaining logistic regression, and this is included in some of your readings for this week. So here they give this example of, do levels of a metabolic marker predict mortality? So here they're saying death, it would be coded as a 1, survival would be a 0, and that's how you would enter it into your database for the analysis. And you can see the definition. So what we're trying to do is we're trying to take this S-curve and make it a straight curve so we can make some predictions. So here's some example data from this particular article, looking at just some relationships between metabolic markers and predicted probability of death. And then here we actually have some logistic regression outputs, which is just presenting the constant. There's no, it has a constant and it just has a single predictor in there of a certain biological marker. Okay, so then what they're doing is they're talking about predicted probabilities. And this model can be used to calculate these predicted probabilities of death for a given value of the metabolic marker. And then they go on to give you some examples. If we input it in, say somebody had a value of 2 and a 3, these would be their predicted probabilities of death based on those values. That you think of those of when you have your regression coefficient, you're earning those as your x, and so you're able to. What they came up with was the corresponding odds of death for these patients. They're able to calculate an odds ratio of 5.4 if they had those levels of markers. So that would say that if somebody had a value of 2 compared to a value of 3. Here's just shows you that when they're looking at some additional tests that go into the analysis is where they'll report these likelihood ratios. And what they did in this particular model was they stepwise entered the variables into the model using lactate, urea, and age group. And the tests are based on the change in likelihood of resulting from including or excluding the variable. And so what this basically shows you is this is essentially like with multiple regression where we looked at that initial ANOVA table and we're saying, okay, yes, this is good to go. We don't know what the effects are or what the odds are, but these things are okay to be kept in the model. And this it goes on with this example. It says we may wish to investigate how death or survival of patients can be predicted by more than one explanatory or predictor variable. And then they ask the further question is, can we predict death with these metabolic markers, urea and lactate, and with age? And then they categorized age as less than 70 or greater than 70. So then what they did is they entered this into a statistical software model, and these are the results that they came up with. And you interpret them the same way in terms of the odds ratios. These are results when you control for all these other ones that are included in the model. So here they have the constant that's in there, like we had with our multiple regression. They included age group, lactate, and urea levels. And so what they found was that for age group, if they were older than, and I believe they coded this as if they're being older than 70, their odds of death were 4.16 times greater than compared to those whose age was less than 70. Their lactate level, it was 1.31 down here. So that tells us for every 1 millimole increase in lactate, the odds of death increased 1.3 times. And you can see the same thing for urea levels. For every 1 millimole increase, the odds of death increased 0.05, or about maybe 5%. This is probably about a 31% increase in the odds of death. And then what you do see is these odds ratios are very precise, so they probably had a rather large sample size in this particular data set. And those 95% confidence intervals are pretty narrow. They also do not include 1, so even if we didn't have the p-values, we know that they are statistically significant. And so here what we can see is we have the constant plus the coefficients that we can then use to calculate the logit of the probability. Same thing as with multiple regression, is they do present an R-squared, the coefficient of determination, and this can help be useful in predicting over how well the model explains the data. It also can be a measure of effect size. So for this particular study, they had an R-squared of 0.17, or about 17% of the variance in death was predicted by age, lactate, and urea, which really indicates that they're not very useful in predicting death. There's a lot of unexplained variance. Then when they did their looked at their cutoff scores, and they looked at some model discrimination using ROC curves. Now this is just an example; it doesn't go with this data. And this really refers to the discrimination of a model, that is how well that model distinguishes patients who survive compared to those who died. And it can be, and that's how we can evaluate that with an ROC curve. And I already mentioned, if it's on a 0.5, then it's like 50-50 chance, whereas 1 is like perfect. So in this particular study, the value they came up was 0.76. And you can see the confidence interval there, indicating it had fair discrimination abilities. It's probably looking something sort of like this one here.